So good afternoon, my name is Petr Kurfürst. I am here from the astrophysical department from the Masaryk University. And the last speaker began to talk about the BE star, so I am afraid that I will replicate his knowledges, which he told you. But my talk will be about these BE stars, which is the specific sort or specific category of the variable star, which is very interesting. And somebody called them bright emissaries. This is a brief outline of my talk, so I briefly introduce the characteristics of BE stars, then I say something about dynamics of single BE stars and the dynamics of binary stars. Okay. And I show something about the so-called disk BE X-ray binaries and other binaries and some observational features of it. So, what is the principle? This is the same what taught my or the last speaker here. So the BE stars are defined as non-supergiant B-type stars. In fact, they are the late or up to early A stars or down to early A stars. Which means the effective temperatures from some 30,000 kelvins down to some 10,000 kelvins, which at least once had Barber spectral lines in emission. This is the schematic picture of the origin of these emission lines of hydrogen, and here is the line of iron. So here is it depends on the line of sight. Unfortunately, the disk cannot be seen here. It is very light, this picture, but maybe you can make it a bit darker or more contrast. No? So this means that here is the oblated star, which is rotationally oblate. Sorry. Okay. Which is rotationally oblate, and here is equatorial disk, which... Oh yes, here is the disk, and if we see the system from the pole, we see the pure emission because the disk emits. And if we see the system more from the equator, so we see this absorption center, which is caused by the disk obscures the star. So this is the main principle of that. And the other characteristic of these stars are that they are very fast rotators, which probably or which is connected with this formation of the disk. But the true detail of the disk formation at the stellar surface is yet not very well known. There are supposed some mechanism, for example, non-radial pulsations or some bright spots or luminosity or super Eddington luminosity and such things, but it is not yet quite certain. But what is probably sure, or in what we are probably sure, is that the mechanism which it is on another picture, that the mechanism which builds the disk is the viscosity, which transfer or transport the angular momentum and mass outward from the star. So there is really created sometimes very large and very extended disk around the star. So here is the illustrative picture of the creation of these emission lines. So we can see here this lambda 0 is the center of the emission line. Here is the blue wing and red wing, which is caused here. It can be seen that the part of the disk which goes farther from us is more red, and which approaches us is more blue. And the typical representatives of these stars are Gamma Cassiopei, Alpha Eridani, Akeda, for example, Zeta Tau, 28 Canis Majoris, and so on. And the principal model which describes the physics of such disk is the so-called so-called VDD or viscous decoration disk model. I said it before that the key role of the viscosity, plays a key role in the transportation of the outward transportation of mass and angular momentum in the disk. So here it is schematically shown that here we are not quite sure what causes the ejection of the mass from the stellar surface, but the viscosity transport the matter farther outward. So this is the principles of the formation of the disk, but such disks are never steady except in infinite time, because we have here in the disk either positive torr, which is the momentum of force, of course, of viscous force, which helps to draw the disk, or if we have no or negative torque, the disk further decays and even may disappear. And this process can be repeated. But it is a very long-term process, so it will be shown later. Here are the basic or schematic pictures of the energetic situation in the disk. So the energetic stability of the disk is supplied mainly by the irradiation from the star. The irradiation heats the disk much more than some viscous forces and other forces which happen inside the disk. And here are some basic formulas. We have to take into account the von Zappa theorem. So when the star is very rotationally oblated and the equatorial parts of the star are much cooler than the polar regions of the star, so the main part of radiation goes from the polar region, and the equator radiates much less. So when we calculate the irradiation, or when we calculate the temperature structure of the disk, we have to take into account this von Zappa theorem, and we also have to take into account so-called limb darkening. Here are the coefficient of this U is the coefficient of limb darkening. So we calculate the irradiation which emerges from the or emanates from the star, and we also have to calculate the irradiation which impinges the surface elements or surface. It has no exact surface, but something which we can talk about, like the surface of the disk. And we make models of this hydrodynamic structure. So here is the example of such a model. I hope I cannot. I don't know how to start this. Yeah, so here's some simple example of the 1D modeling of the hydrodynamic structure of the disk, where we have the blue line is the 1D slice of the disk density in the equatorial plane. The red line is the slice of the radial velocity, which, as we can see, grows in the more distance from the star, and the green line is the rotational or Keplerian or almost Keplerian rotational velocity. So these are the 1D slices. Okay, we can go on. Here I show something about the 2D structure. So we also modeled self-consistent 2D structure of the disk. This means that self-consistently we calculate the density, velocities, temperature, irradiation, and radiative cooling of the part of the disk. So, can we start this animation? So here is some schematic video how this way. So here we can see that this is the density structure in 2D model. So here we can see the converging density wave, which recalculates the structure of the disk according to all the conditions which we input as initial and the boundary conditions. Okay, so go on. And here are some results of the 2D modeling. These are examples of the structure of the disk, which has, when the stellar mass loss rate, this m dot stellar mass loss rate is about 10 to minus 8 solar masses per year. And here is the same mass loss rate, but here is different so-called alpha parameter, which is the parameter of viscosity. So when we have the low viscosity, here is 0.1, the disk is approximately smooth. But in case of high viscosity, when alpha is 1, the disk is not so smooth. However, it shows the periodic density wave. It is not stable in this case. It shows the periodic density waves, which may contribute to some short-term variability. But here is the model done by Xavier Hobois, where they calculated the creation or the time of the creation of such a disk via this formula, and these numbers are years of the creation. So after some 50 years, it would be extended up to some, I don't know, here is some 70. This horizontal axis means the radius over the stellar radius. So it is the radius in terms of the stellar radius, and here is the surface density. And so it may be 50 or so stellar radii. Here is 100, but the thick black line means that the time goes to infinity here. So after infinite time, the disk would be stable according to this model. But this will not happen because sooner the disk will also decay or dissipate. So this is the basic characteristic of the disk, that they are not or never steady. And here are some observational results done by Mohammad Qureshi this year. And here are the curves or light curves of the secular long-term variability, which is caused by the growth and dissipation of the disk. So we can see that for example, here is the apparent magnitude of the star. This gray strip means the intrinsic magnitude or intrinsic brightness of the star itself without the disk, and this is the contribution of the disk. So we can see that it is more than 1 stellar magnitude, but when the brightness goes down, it is about half or so stellar magnitude. It is the case of the star Omega Canis Majoris, which is one of the most bright BE stars in the sky. So you can see that this apparent magnitude is about 3.8 or so. Here are the stellar parameters. And here we have another case, which is for me much more interesting. And this is the case when the stars are not single, but are in binary systems. So the main, or the most of the stars, which BE stars, which are in binaries, are so-called B X-ray binaries, which means that the central star has a companion, which is in most cases the neutron star. It is a neutron star, and it is maybe interesting in this sense that we know how the neutron star is created. So this system survived the supernova explosion once. These B X-ray binaries are the very bright sources, but not so much of the visible light, but from the of the X-rays. These are very bright X-ray sources, and this X-ray emission comes from accretion of the disk material onto the neutron star companion. It will be seen a little later how it works, and these are the parameters of the orbits. They are very often quite eccentric, and most of the systems show only transient activity, so they are active only, for example, when they go through the periastron passage, and in the meantime they are inactive. And here we have three types of X-ray activity. Either it is low luminous, it is not so interesting for us, but there are very dramatic periodical outbursts. We call it type 1. It means that this Lx means that it is luminosity in X-rays, 10 to 35, 10 to 37 ergs per second. And these type 1 outbursts are periodical, and they are connected with the orbital period of the companion. For example, they occur during each periastron passage of the companion, and except type 1, there are also type 2 outbursts, which are much brighter, or are brighter, and they during a longer time than the type 1 outbursts, and are non-periodic. These are unique events. So here's some picture or some measurement of these type 2 and type 1 outbursts. So you can see the type 1 are periodic. Here is the daytime in days, so the duration of these periods is about, 50 days or so. But it is connected, as I said, with the rotational period of the companion. And here is the example of the type 2 outburst, which is much longer, about 100 days, and much brighter in the X-ray. In the X-rays, so type 1, and here is the schematic picture, or a picture of another characteristic of these binary BE star systems. Here the neutron star orbits in an eccentric path, and the disk is then truncated due to this orbiting neutron star, and the truncation is in most of cases, the rotation is on radius which is about 3 to 1 resonant radius, which means 3 to 1. It means not in radial distance, but in the time of Keplerian orbit. So, and this resonant truncation works as well for the misaligned system. It means that this orbital period is not in one plane with the disk. It may be somehow inclined, of course. So it works well even in this case. And here are something about we try to model this physics of this neutron star accretion and the neutron star radiation. So we have to, of course, use some simplifications, and the basic simplification is called the Bondi-Hoyle-Littleton approximation, where the neutron star accretes from such radius, where these characteristics are described here, what they mean. And here I said that this is a 3 to 1 resonance radius, which means 3 to 1 in the period of in time of period, and the distances are approximately in the ratio of 0.42. And if this accretion radius is higher than so-called disk scale height, or scale height, vertical scale height of the disk, So the neutron star in this case accretes all the material, and the X-ray luminosity may be expressed due to this formula. And we can calculate, because this X-ray luminosity can be known from the measurements, so we can calculate this m dot, which is the mass loss rate of the stellar system. Here is some table of the stars which we modeled in this way. So here is the spectral type. Everything is B-type star, and here's the effective temperature of the star, so 24 kilokelvin, 24,000 kelvins, and so on. Here is the radius in terms of the solar radii. Here is the so-called binary parameter, which means the distance of the companion, or the average distance of the companion from the central star in terms of solar radii. And here's the X-ray luminosity in ergs per second. And here is some results of our models where we calculated the temperature. Here is the convergence of the density structure, including the neutron star in some distance. Of course, it is simplified, so we expected co-rotating and aligned system here. And okay, we can go. And and here are the pictures of the temperature structure. Here we model the temperature structure using once again the self-consistent model. So we model together the density structure, irradiation from the star, X-ray luminosity. The irradiation we calculated using some mathematical methods which are called long characteristics. And here is the example of the star GRO J1008. So here are the parameters of the star, and here is another example of another star, HD 215, and so on. So here are also, once again, the parameters of the star. So we calculate the model, and from this model we can calculate the mass loss rate of the system. And here's some brief remark about the BE disk in other types of binaries, which may not be the B X-rays, but some common binaries, and which are the other features which cannot be observed in isolated stars. So there are some types of the disk variations, for example, so-called VR variations, which are caused due to the arms in the disk in binary system. It is similar to the arms which are, for example, in galaxies. We know that galaxies, or some types of the galaxies, have arms, so they are also arms. Also we can describe the precession and warping of the disk in this binary system, which also contributes to the variability. And here are some here are some pictures of measurement of Petr Kurfürst in this stellar system B2246 Cygni. But it is as I told, it is the X-ray luminosity, not the visual luminosity. Here are the soft X-rays and hard X-rays, which are classified approximately up to 5 kilo electron volts are soft, and over 5 kilo electron volts are hard X-rays. And it is expressed in such strange units, crap. It is connected with the Crab nebula, and it means the X-ray activity of the Crab nebula, and so on. But it is 2.4 times 10 to minus 8 ergs, and so on. It is the same as 2.4 10 to minus 11 joules per meter squared. And here we can see that the difference is about 0.6 of this Crab. And another example, there will be also, here is even 0.8, almost 1 Crab, and such analogy, which is of course not perfect, but if we if we compare it with the visual light, so the difference in visual magnitude should be 5 magnitudes. So this X-ray variability is very high. And here are some light curves of the system, of the same system. And here is the example of this type 2 outburst, a type 1 outburst. But in soft X-rays and in hard X-rays, but the vertical scale is not same. Yeah? It is too small. But in this hard X-rays, it is about this one crab, which could mean, analogously, it could mean 5 stellar magnitudes. It is slightly less. And the period is, once again, about this 50-day, or I'm not sure now, but 39, yes, this is 100 days. And this is a similar picture of the system GRO and so on. So it is slightly less. This difference is slightly less than in the previous system. So conclusions, this long-term photometric variability which occurs due to the growing and dissipation of the disk may go up to some delta of the visual magnitude up to 1 magnitude, and of course the presence of companion, or the case of binary system, is much more interesting and much more complex than the single BE stars. This I told about the disk truncation, and in these B X-ray binaries, the accretion rate increases with the eccentricity of the companion orbit, and we know that highly eccentric and rather coplanar systems are much more favored for this type 1 X-ray outburst. And what is the big mystery up to now is the mechanism which provokes the type 2 outbursts. We don't know exactly what is the reason for this type 2 outbursts. So thank you very much.